Hey everyone, welcome back to another practice problem video here. So in this video, we're going to be just doing some practice on linear approximations. We're going to use both methods we discussed and sort of just do some practice to get a feel of how they might apply in the context of different problems. So like always, I will do these problems out thoroughly, so feel free to skip through and see as you need. There's a table of contents in the description that you can use to navigate through this as well. All right, so that said, let's get started. So we need to approximate ln of 1.2 using the tangent line method. So what's the first thing we need to do? Well, first thing we need to do is we need to find a known point close by. We need to find a known point close by. Okay? And this is just for us to get a reference frame that we can use to figure out our tangent line and all those sorts of things. We know that the natural log of 1 is 0. So therefore we can use that as a good reference point, I think, right? So this is a good place to start, and therefore we could say that we're going to use x equals 1 as our known value, okay? So that's where we're going to start from. And this also gives us the coordinate. This gives us a known coordinate of this line, which is 1, 0. That's not useful to us right now, but it will be when we have to write the equation for our tangent line. Okay? So we have a known point, and we have that coordinate there. That's what we have so far. Next thing we need to do is we're going to need to start building our tangent line, right? We're going to need to start building our tangent line. And so what are the components we would need in a tangent line? We have y equals m x minus x1 plus y1. So let's see what we need to find. Y and x are just going to be variables. We don't need to do anything with that. x1, y1, that's a known point that our line will pass through, okay? And m is going to be our slope. Now, how would we find m? Well, we're going to take a derivative. And a known point, there we are. So all we need to do from this point on is just find the derivative, okay? So let's go ahead and do that. Derivative. Sorry for my sloppy handwriting, but hopefully you can see what that means. So we're going to need to take the derivative of the natural log of x evaluated at x equals 1. Why at x equals 1? Because again, we're trying to find the slope of the line. We're trying to find the slope of the tangent line at the point x equals 1. And why at x equals 1? Because that's our known value close to x equals 1.2, right? So this is just going to give us, this is an easy derivative, so it's going to be 1 over x evaluated at x equals 1. And if you plug in the 1, you're just going to end up with 1. So that tells us that the slope of our tangent line at x equals 1 is going to be 1. Okay, that's the slope of our tangent line. Now we have all the components we need to find our tangent line. So let's just put them all together here. So we have y equals 1 x minus, we have another 1 over there, and then we have another plus, we have a 0, but I'm just going to go ahead and ignore that. So we just have this as our final equation, okay? So that's what we've got our tangent line here. Now the last thing we do is we're just going to go ahead and evaluate. Okay, we're going to go ahead and evaluate this. We're going to go ahead and plug in 1.2 into this, and we're going to go ahead and try to figure out what our approximation would be. So we'd have that y equals 1, 1.2 minus 1, which is going to come out to 1 minus 1.2 is 0.2, and 1 times 0.2 is just 0.2. So that's our approximation, okay? And now let's see what the true value would be. The true value would be is 0.18 2315, whole bunch of decimals. But as you can see, again, those are really, really close. So they're very close. So as you can see, we have a good approximation. So this is a good approximation. So therefore, we've done our job. So we've got a good approximation, and we've done our job there. So again, we have to find a known point. And then we need to start building our tangent line. So we use that point, we'd use our derivative, and then we'd set up our tangent line and just plug in the value to figure it out. So that's how we'd approximate using the tangent line method. We're going to approximate the value of 82 to the 1/4 using the differential method. Now this looks really, really scary because, 1/4 power, all that stuff is not something that's really easy to deal with. So here's what we're gonna do. So we're just gonna follow our known steps, but this time we're gonna use the differential method. So it's gonna be slightly different, but the steps are still essentially the same. First thing we need to do is we need to choose a known point to be our reference frame. Okay, so our known point is gonna be x equals 81. Why x equals 81? Well, if you take the 4th root of 81, that comes out is equal to 3. Because 3 to the 4th is 81. So therefore we can use x equals 81 as our known point. And of course x equals 81 is really, really close to x equals 82. Okay? And our function, of course, is going to be the 4th root of x. Now the next thing we need to figure out is we need to figure out what our derivative is. Right? Because once we have our derivative, we can just use our formula and begin solving for things. Okay? So our derivative would be d dx of x to the 1/4, and we're going to evaluate that at x equals 81. Yep. So this would give us 1/4 x to the negative 1/4 evaluated at x equals 81, which is going to be 1/4 times 3, because x to the negative 1/4 is basically just going to be 1/4 times x to the 1/4, right? And that's just going to be 1/12. Okay, so that's what our derivative would be. Now we're just going to go ahead and use a formula. And that is going to be f of, let's see, 82 is going to be f of 81 plus f prime of 81 dx. And of course that dx is just the difference between 82 and 81, which is just going to be 1. Okay, so this is going to end up being 3 plus f prime of 81, which is 1/12, 1, which is going to be 3 plus 1/12, which approximately evaluates out to 3.0833 with recurring decimals. And what's the true value? Well, that's going to be 3.009216 blah, blah, blah. So again, these two are really close. In fact, the degree of error has decreased even further from the previous problem. So these are very, very close, which is really good, because especially because you've got a whole number out here, the fact that your error only comes in like the second or the third decimal place, that signifies a really good approximation. So therefore, this is a very good approximation. Right? So again, we figured out our known point, we figured out our derivative, and then we plug all those into the formula. It's a very straightforward idea, but sometimes it's just a little bit tricky to see. But again, whenever you're doing these, all you need to do is just think about all the pieces you need and how you'd get them, right? So to find f prime of 81, you need a derivative. To find f of 81, you just need to find a known point close by. And if you weren't able to figure this out, then it's a good idea just to like throw random numbers out there. Just try to see what works, right? This is not something that there's a formula to figure out. It's just something you gotta eventually know, right? So we need to approximate the square root of 2 using the differential method, okay? Again, we're just going to follow the same steps. So let's just write out our formula first, actually. Okay, f of 2 is equal to f of, I've left that blank because we need to fill that with some known value, which we're going to figure out in just a second. We need to figure out some known value. So what do we know the square root of that's really close to 2? Now the first thing you might think is 4, but actually if you think about it, we know the square root of 1. And 1 is awfully close to 2, right? So we're going to use 1 as our reference point. And why we can do this is again because we know that square root of 1 is equal to 1. Okay? So that's going to be our known value. So we're gonna say that f of 2 is equal to f of 1 plus f prime of 1, and our dx is the difference between 2 and 1, which is also going to be 1. Okay? So that's what we're going to do now. Our second step is we need to find our derivative. Right? And what's our derivative going to be? Well, we're going to need to take the derivative of our general function, which is the square root of x, evaluated at x equals 1. This ends up being 1 over 2 root x, or 1 half x to the negative 1 half, same thing, evaluated at x equals 1, which is just 1 half. This is actually the same function we used in the theory video, so you might remember this as being familiar, right? Now let's just plug everything back in. So f of 2 is equal to, what's f of 1? That's just going to be 1, right? Plus f prime of 1, which is 1 half. Dx is going to be 1. That's going to land up being 1.5. Now let's see what the true value is. $1.414 2, 1, yada, yada, yada. And again, as you can see, these are close. These are very close. So again, we have a good approximation. So that tells us we've solved this problem correctly. And I hope you're kind of seeing how we get this all. So this is our known value, right? That's our starting point. And this kind of change is what's really going to determine the accuracy of our value. So we're just tagging on that little extra change that we can use to get us within a reasonable margin of error of our true value, right? So yeah, there we go. That's our practice problem video. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time.